My name is Didier Queloz. I'm professor of physics. Welcome to my exp. To understand how much a breakthrough it has been, the discovery of the first planet, we have to go back in time. We have to go back at the time when there were known planets. So it means I have to go back to the 90s, essentially here. And in the 90s, people had a pretty good idea of the formation mechanism that would lead to the solar system. We had a good model to understand the formation of the solar system, with the small rocky planet near the stars, and then the big giant planet full of gas, essentially the same kind of gas you have in the sun. The astronomers were very eager to detect other planets with the idea they would kind of look in a similar way to the solar system. The challenge here is, how do you detect a planet? Well, star is easy, but planet is challenging. Not because it's small, it's because it's next to something very bright and very big. If you look in the infrared, which is the best way to detect a planet, the sun is 1,000,000 times brighter. And if you look in the visible light, the one we see with the eyes, is 1,000,000,000 times. It's really huge. And we have no ways to see planets. So we have to rely on indirect techniques where we look at the star and we find on the star whether we have evidence of a planet. And one of these techniques, what's called the radial velocity, where you observe the possible change of speed, radial velocity, speed of the star, that would be related to an orbiting planet that would essentially push and pull the star on its orbit. Michel Mayor was doing radial velocity program, not for planets, for studying binary stars, for studying the galactic evolutions. And he had an opportunity to build a better instrument, more efficient, in collaboration with the Observatoire of Haute-Provence, that wanted also a spectrograph. That's the name of the machine, to measure the spectra and to compute the speed. And that's how I came. Now, at that moment, there were no idea of detecting planet. The machine was not really designed to get super accurate. We wanted more accuracy, but not exactly the accuracy for a planet. Starting my PhD was fun, working on new instruments, and I really dived in. And I took the challenge to do as best as I could do to push this machine to the best accuracy. It took me a bit more time. A usual joke with Michel, he thought I would take 6 months to do it, and I took 3 years, but at the end I got a machine much better than what he had in mind. And what it was critical here, we realized the machine had this very magical precision, which is about 10 meters per second. And 10 meters per second for us, it rings a very interesting bell, which is the effect of Jupiter, our own planet, on the sun. So at that moment, we were aware the machine we had built, which is called LOD, could detect objects as small as a planet. But of course, everybody had in mind the solar system. So it would take years, and when the program started in '94, it was obvious for all of us, including Michel and myself, that I would never ever detect a planet. Now, the end of the story didn't turn out exactly the way we thought, because when alone at the telescope, one of the stars was 51 Pegasi. It was one of the stars. We had about 140 stars. It was one of the bright stars. We have 20 stars a bit brighter than the other. That's why I started measuring this one. And then what I saw at the telescope was very strange. And strange is really a weak statement. It was a bit of a panic moment when I realized that when I was measuring the speed of that star, the star kept changing. They should have expected to stay the same number, same speed, because in the galaxy they don't change. They only change if there is something orbiting very close to the stars. And we know that star, we're not supposed to have another stars, and so, such a star should have been a stable star. And then I kept measuring it, and I really thought something was wrong in the machinery. I made a mistake somewhere. It was a new program, that tons of lines of codes, and in these days it was a Fortran. It was kind of a complicated program and complicated instruments, brand new for everybody. The chance it would have been a mistake was very high, and I worked really hard to understand what was wrong. Well, after a couple of months of work alone, because I was a bit scared to talk to Michel about this, I thought it was my mistake, so I had to find out. I had to realize that there were no mistakes. I was real. Now, to push my understanding, I try to find out some logical pattern there. Usually when you do that, you look for a periodicity. I found a periodicity. It took me some time to find this. It took me at least 6 months altogether to get the understanding of this data, because you don't always have access to telescope. You have access for 1 week, you come back in 2 months later, and so on. So it's a long sequencing of event here that took me from 94 to 95 into March 95, when at that moment I thought I had a great orbit. And to my big surprise, the orbit was 4.5 days, a bit less than 4.5 days. But the corresponding mass you would compute from the amplitude would be less than the mass of Jupiter. I found a planet that was completely awkward because there is no planet like that in the solar system. Jupiter takes more than 10 years. And then I sent the information to Michel at that time. I thought I had enough material to tell the story. We worked together on this data, and he had to admit that what I've done, what I did at that time was fine. There's nothing else we could do. And he was so skeptical about all this. He said, well, I can't believe that. We have to reobserve. And we did what any good scientist should do in any case like that. We make a predictions. We call that an ephemeridis in the orbital world. And I predicted the speed in the summer, 95. The star was behind the sun at that time in the spring. So when the star 51 Peg came back, we were at the telescope together this time with my data, my spreadsheets, and every night, you know, it's like a game. You have the prediction and you measure the speed, and you say, oh my God, this much. So you do that for the first night. You say, okay, it's lucky. You repeat the second night. You say, well, it's still luck. The third night, I say, well, it becomes more than luck, but we have to be very careful. We waited the fourth night of observation where the prediction, we're matching the data to say, okay, that must be real. And at that time, we realized we had a big problem because we had the confirmation that the data were right, but then in front of us, we had the community. First, to demonstrate we had the first planet. That was a field where a lot of fake news had happened in the past. It was a minefield really there. So we know we had trouble already on that aspect because people are skeptical by construction in this. And then the worst of it, we were detecting a planet that nobody was expecting. And by the way, we have no way in terms of the theory of planetary system, the way we understand from the solar system, to explain it. I think for me, it was awful. I think the couple of years that came after discovery was a very ugly moment for me because essentially we were pushing into a story that very few people would believe because it was so transformational. It was so new, so different from what everybody would expect. It was too much ahead of its time. It took 4 years essentially until we had the first transit. So one of these hot Jupiter had the right angle, HD 209458, to produce a transit. From 95 to 99, we had maybe a dozen of planets detected, not us, but also with our colleagues, American colleagues. And then at 99, then it was obvious they were real. This has completely changed the field for a couple of reasons. The first one is we demonstrated they are a different kind of planet than the solar system. And then the field kept expanding the same way. We kept detecting planets nobody was expecting. And actually we know today that the vast majority of the planetary system are much closer to the star than we are in the solar system. So the vast majority of the planet would fit within the orbit of Mercury in our own solar system. And we have a huge diversity, much more than we expect. We don't only have the rocky, the giant, and the ice giant planet. We have a whole range of planets that we tend to call them mini Neptune, super Earth, that just show the diversity of the structure, which is related to the diversity of formation processes that is happening for the formation of planets. Well, scientific discovery, it's a big topic. I think the story we went through is very rare. Science is rarely done like that. Most of the science advance, and I think it's better that like that, are made by small steps. So in a way, you know, and you just push a bit better, and you change a little bit, and you just evolve gradually. So it's more like a step change to evolve the knowledge. It's very rare when you have, let's call it a crisis, when you are really changing the baseline of the field. It happened in the past. Physics had its high days, I would say, in the past centuries, when a brand new physics happened. Quantum mechanics, the relativity theory, all this was brand new physics, and that opened a complete new field of discovery. But most of the time, you know what to do, and you know what to expect. So what we had to go through is something that was not expected. So how could you then do that in science? Because simply science is not about theory. Science is about facts. And when the facts are telling you another story and you're sure about your fact, well, you have to revise your understanding of what the universe is. And that's exactly what has happened to us. You had an idea what a planet is like, but you have a too strict idea what it must be, and when you start looking at the data, you realize that this is much more complicated than what you thought, and then the whole theory, the whole concept of planetary system has to be reprocessed. And whatever you're dealing with in science, you always come back to the data, because that's the only thing that survives the time. There is not a single theory that have not changed. Even the very best one, you go back to Newton, we're still using it, but we have to change it many times because it's not applicable. We know that in some conditions. If you go too small, it doesn't work, it's quantum. And if you start dealing with more mass and more speed, then you have to bring up general relativity. So any theory is wrong to extent, or it's just reflecting the data you have been using to build up the theory. And this is all about that. Science is data driven and trying to make sense to the universe on the basis of the data you can collect. Quite often I got asked what is to be a good scientist. The only thing I know is to look at myself and to look and try to understand who I am and the kind of work I'm doing. And there are certainly some elements in my life, in my own psychology, which I think is part of a success, why I became a scientist, a professional scientist. And I think one of the elements which is key is, let's say, curiosity beyond average. I would say it's not normal. I used to sometimes mention it's like a soft disease. You are really curious. You really want to understand everything. When I say everything, it's really everything. It has no boundary. I am also very interested about social psychology as I am in physics. So there is this idea that things make sense, and if you work hard enough, you can understand what it means. And that's very profound into me. I don't know why, but that's who I am. So when I wake up in the morning, I feel my day would be fantastic because I will learn something. The day is about triggering my curiosity. And there is something which is very magical. My body is getting older, but my mind, I get the feeling I'm exactly in the same mindset that I was when I was a teenager. Maybe I have more knowledge now, and my brain is a bit more damaged than it was when I was younger. But this energy of understanding, I think, is something very profound. And sometimes I compare it with an artist that, or a writer that have to write. And that's just a matter of life and death. And it's like for me, this is why for a scientist there is a word which is a taboo, which is retirement. I think we can't retire, it's impossible.